fatigue of composite materials. So we have the speaker, Professor Vassilopoulos, with us, who will be again spending 2 hours today with us. I will have one lecture session from my end after 1 hour. That means at 3 o'clock IST and 10:30 CET. After 1 hour of this lecture, which will be on basics of fatigue of fiber reinforced composite materials. I will talk about some very basic issues, and then one or two material systems that we have tested in our laboratory here. I'll also touch upon the facilities, the basic facilities which we have in the lab for the participants who want to set up similar labs in their institutions, or they want to do research related to composite materials, specifically fatigue related research. So they may have an idea regarding what to expect, what may be the basic things required in an Indian setup to start this particular research. We cannot compare the facilities with the EPFL, though, because they are too advanced and too many, which are quite difficult for all the Indian institutions to afford because of the cost issues. So we will talk about something in my presentation. So I now hand over the today's session to Professor Vassilopoulos for starting his talk.
Thank you very much, Raman. I will discuss today about modeling techniques, following up the discussions that we had the previous days that were mainly related to the introduction of fatigue and also experimental investigations. So mainly today we'll see how we can use this experimental data to develop modeling, theoretical modeling or numerical modeling approaches, and how we can also use in a second stage these modeling tools that we have to perform some prediction of the performance of the composites in their lifetime. So in reality, what we can see in the literature is two types of modeling techniques. What I have here in the blue frame and the red frame, we have modeling techniques that are used for simulation of behavior, that can be also used for the understanding of the performance of materials and explain why and how materials fail. And this is what we call descriptive modeling. And we also have tools or theoretical models, if you like, that are used for predicting. What is a bit challenging is to identify these two types of models. And actually in the literature, we've seen a lot of cases where this terminology, if you like, has been abused. And when I say abused, usually it is abused on the way of kind of upscaling the capacity of our models. We've seen a lot of publications talking about prediction, although they are only kind of limited in fitting, in description. So there should be a bit of care and we should try to use the models correctly and define them correctly when we expose the models. So the modeling and prediction in fatigue is based actually on experimental data, on the investigations that we do in the experimental halls. And this data that we have can be able to describe. We've seen yesterday a lot of Hessian curves that describe the lifetime of a composite material. How does it fail, when actually it fails under different stress levels. And in some cases, these models also help to understand the behavior of the material. And this is mainly done when we talk about models that are related to damage mechanism. A simple case is the models that are related to fracture mechanics, where we follow actually a crack or several cracks, and we actually understand that the fatigue behavior, so the fatigue failure is due to this damage mechanism that are activated. So the models that we have actually they are used to fit the material behavior. And I highlighted the word fit here because actually it's a fitting, it's a simulation of the behavior. It's nothing more. And these are the models that we mentioned in the previous slide as the descriptive models. We have also the predictive models with the aim, the objective of these models is actually to estimate, so simulate again the material behavior, but under loads that are not seen in the development phase. So there it's this type of models can be of any origin, and they are not necessarily models that describe and let us understand the fatigue behavior, but might be models that are based on experimental evidence. So these models are called phenomenological. They are based on the description of phenomena and the expectations that we have or the experience that we have on the development of synergistic, if you like to call it like that, activity of several or appearance of several phenomena. So the objective of modeling approaches, of course, it is understandable by all of us. They are very helpful. They help reducing the number of experimental campaigns that we should set up to understand the fatigue behavior of composites. They can be used for reducing also testing by developing virtual testing environments. We have models that can predict the behavior of the material at different conditions, so we don't need to test the materials in these conditions. And they can be useful for the simulation of the response of the material, lifetime estimation if they are predictive models. They are also interesting in the case of the potential to do this progressive damage modeling, terminology for PDM that I have here, the acronym, where we can go and actually predict the eventual material failure by identifying the intermediate damage that we can see during the fatigue life. And also models, if they are validated, they can be used for material selection, which is also very interesting in design approaches when they models give the opportunity to the designer to select different materials, run the modeling techniques that they have in place. So actually, this is related to virtual testing of the composites, estimate fatigue life, and in this case, by doing an iterative procedure, be able to optimize actually the material selection to have those materials that would give a structural component or a structure that has the best performance. And this, if you remember in the first day that we were discussing about the validation of the design, having this procedure in place, the material optimization through theoretical predictions, can help reducing a lot the cost of a design procedure by reducing a lot the need for full-scale design verification procedures. So in descriptive modeling, we mainly have methods that rely on experimental data. And in the literature, you will see mainly those methods that I'm describing, I'm listing here. So the S-N curves that we have already seen more or less. Theories that are based on stiffness degradation. We discussed a lot about stiffness degradation, but we didn't say how we can model this behavior. And theories that are based on the residual strength. If you remember from the discussion that we had yesterday, residual strength is the strength of the material after having assumed a certain number of fatigue cycles. So if we have a model to estimate how this strength is reduced with the fatigue life, then we can certainly give some assessment of the remaining lifetime of the material. Some of these methods that I'm listing here, like for example the CLDs that I have them with the star there, are also used for predictions. So we can have CLD to describe the properties development with time, so to describe the material performance. But we can also use CLD to predict the behavior of the material under different conditions. So in case of CLD, different R ratios. We will see later on how we do this. So the S-N curves and CLDs, I will just now go through these three categories of materials and describe a bit all of them. So actually, as we said before, S-N curves and CLDs are empirical methods that are relying on experimental data. We get the data and we fit the data, and we can get, if we fit the data, we have a curve. It's obvious. And then we call it the S-N curve when we fit stress life data. We also have the similar curves when we plot strain versus cycles on the what we call the epsilon n plot. By the way, strain life plots are very common in the cases where we care a lot about low cycle fatigue. And it is also common, these epsilon n curves are also common in metals. So when we have these S-N curves established, we can build the constant life diagrams. And having the constant life diagrams, we can have a full impression, an idea about the behavior of the material over a wide range of R ratios, so of different loading conditions. So S-N curves, they are simple representations. They have no physical meaning, as we said before. And based on that, although we know that all S-N curves have a similar trend, but we can imagine that the best S-N curve, since there is no physical meaning, is an equation that fits better, so it gives the better fitting accuracy for the fatigue data in all fatigue regions. So the S-N curve is a very easy way to describe the fatigue behavior. What is also interesting for S-N curves, and that's why probably in all the fatigue investigations of composites, the first output that we have is an S-N curve. It is like that because it's very simple to record the data. As we discussed yesterday, we just need to record the number of cycles after which the material fails under a specific loading condition. And usually in fatigue, we draw these S-N curves. We try to develop S-N curves in a region of cycles between more or less 1,000, so 10 to the power of 3, and 10 to the power of 6, so 1,000,000 cycles. Specific applications might need more or less. So materials used in wind blades, for example, we know from aeroelastic measurements that the wind blade material can see more than 10 million cycles during their fatigue life. So there it is probably interesting to do testing at the high cycle fatigue and reach 10 to the power of 7, even 10 to the power of 8 fatigue cycles during the experimental investigation. And this will allow to avoid problems with poor modeling due to extrapolation into unknown spaces. You can imagine, and now we'll start with my excellent drawing skills. You can imagine that if you have stress and number of cycles, you have your data here, you have your data there. If you can say that here is 10 power 3, 10 power 4, 5, 6, and so on. If you have your data there, you fit your line, you don't have data at this region, but if you continue, you assume that your line continues the same trend, then you can predict theoretically data in this region, but you don't have any data to validate this. So this might lead to modeling that it is falsified. So depending on the needs, where our application, where the material in the application is expected to operate, it is then this knowledge allows to define exactly the range over which we would like to do, preferably, if you want to say like that, we would do experimental investigations to get the actual material behavior in this range. So it is difficult to get data. It is difficult to get data in the high cycle fatigue because of the time that is needed there, and also because the line becomes flatter there. Sometimes we see that there is more scatter in this region, and the situation seems easier for low cycle fatigue because there you just do a test and in a couple of hours you can have your result. But there I have this question mark. It is easier in low cycle fatigue, but it's not necessarily easier because of several reasons. And one is the reason that we already discussed yesterday, and we also spent a lot of time there, is that at high stress levels, we need to fix the material well. So we need to grip the material well. So we need to probably increase the pressure in the grips. And we've seen also because of the high stresses, we have stress concentrations that in several cases lead to significant number of tab failures. So failures that are not accepted in fatigue analysis. So to respond to this question mark there, at high stress levels, it is faster to do testing, but it's not a guarantee that it is also easier to collect an appropriate number of valid test results for low cycle fatigue. What can improve this situation, these difficulties that we have there, is to include the static strength data in the analysis. We've seen methods that help to use static strength data, but there we should be very careful to consider, to take into account the differences that we can see in the lifetime of the material because of the different strain rates. We've seen yesterday that strain rates in fatigue are usually much faster than strain rates in static testing. So if we don't have data that correspond to the same strain rate, especially for composites that are viscoelastic, then we see that the fitting is quite poor there. To show this difference between the behavior of the material in static or fatigue loading, we can see that in a lot of for a lot of materials, the actual behavior shows that the SN curve flattens at the low cycle fatigue region. This means that the SN curve actually of composite materials does not have a continuous trend of a power curve, does not have the same slope in all three regions, but it is actually segmented. And at the low cycle fatigue, it has a lower slope that becomes higher and probably continuous until the high cycle fatigue after a kind of transition region in between. We discussed this change in a publication that we did in 2012 with one of my previous PhD students. So we already agreed on this, that the best SN curve is the one that fits better the fatigue data. And then if we go and see during the years what happened with SN curves, we can find a lot of methods that have been developed and proposed after this Basquin method in 2010. We have a multitude of models proposed for the analysis of, so actually the fitting of the composite materials stress life data. And in this case here, I just mentioned some of them. The typical linear regression curves, so power law, logarithmic, those that are described in the ASTM standards. Then we have another class of curves, these statistical based methods. Results of this, or examples of this, we've seen yesterday with Whitney and Sendesky wear-out models. We have the curves that are based on polynomial fitting that have been introduced by the group of Harris and my group in the past. And we also have methods that are based on the analysis of the fatigue data by machine learning techniques or artificial intelligence. And there we had also in the past a lot of approaches for that, mainly for modeling. And we see also the later years. So this has been to give you already an introduction about these machine learning techniques for fatigue analysis. We worked on that around 20 years ago. Then at that time, we had quite limited access to machine learning tools, mainly in neural networks, genetic programming, ANFIS. And at that time, we published and we proved that these methods can be used for composites fatigue. And now lately, with the next generation of machine learning tools that we have today, there is a new wave, if you like, of analysis and publications that are appearing here and there for the use of now new tools for the analysis of fatigue data. So what is visible in these plots here is that any selected method, whatever is the type, can be potentially useful and valid for fitting the experimental behavior of composite materials. So coming back to this interpretation is that there is no best SN curve in reality. The best one is the one that fits your data best. So we know, we discussed yesterday that we have scattering composites. And if you remember, we said that in composites, experience show that kind of a decade of life, so between 10.3, for example, and 10.4, it is a scatter that is acceptable. So we should expect to have scatter in our experimental investigations, and we should not impose, if you like, low scatter in the testing. And the question here is, if we observe low scatter, can we be always happy without questioning why we have a lower scatter? Do we say, okay, the scatter is low and the results are very, very well executed? Can someone, after these 2 days of our meetings, give any response to this question? I will start with that. So low scatter is good. Sorry. Okay.
The low scatter standard deviation and variance, if you have the low sigma by mu, I think that's a good coefficient of variation. COV is less, then it's a good experiment, I think.
So if you have low scatter, is a good point, huh?
Yeah, and just normal. That's like normal thinking, but for this case, yeah, that's an expected line of thought.
So I agree with this, and this is the main objective, to reduce the scatter as much as possible in fatigue testing. The problem is, if this low scatter...
Sir, I have one question.
Yes.
Sir, the diagram what you are showing in this particular slide, how can we say that the data, the experimental data what we are getting is statistically significant? Because this question always comes while we compare two materials or these kind of treatments, that how that two data are different. Suppose we take some particular load, although while doing the curve fitting, our one curve is higher than the other. But suppose we take one particular stress level, then at that stress level, we find, because of that large scatter, if we see the statistical significance, if we conduct T test or T test, then it does not become significant. So although the curve fitting is giving a higher curve or a lower curve, or some changes in the slope of the curve, but if we see at a particular stress level, then data are very near to each other.
So the statistical significance of a data set can be examined by tools that we have in statistics. So you have this goodness of fit test that you can apply in your distribution and see if your data is statistically valid. So there, for example, in your question, if you fit a distribution to this data set, then there is a second test that you can do there, which we call it a goodness of fit test. Shows if this statistical distribution that you are fitting fits well your fatigue data. And then if you fit well your fatigue data, it means that you have a data pool, a sample, that is statistically correct.
Sir, as I can see in this figure, that the blue points are much higher than the black and red points. So it means that in the dry condition, a lot more tests are conducted than the dry sample and the wet sample. So if we see around 22 or 24 megapascal, the blue points are much at like 100. First point we can see is at the 100, and if we see that it is around 12,000 or something, the last point. So, but the red points are in between these points. But we can see that the red curve is well below the blue curve. So how is it justified actually? Suppose I want to, although the curve, we can see the curve fitting or the R square value, maybe it is not mentioned here, that it is giving good fit. But even then, for a particular stress level, we cannot say that the data is statistically significant. Suppose we conduct more tests in the dried state, then we might get the similar scatter and the curve can go up or go down.
So at this stress level,
So how can we conclude?
so
Yes, yes, yes. I'm talking about this.
at this stress level, the blue data for me are not in a good how can I say, in a good format, or this is, to say it in a different way, this is a scatter that for me is too large. So there,
Yes, yes.
I would think, if I see this data, that something special happened at least with this point here, with this specimen, and this specimen failed prematurely. So if you remember yesterday, the data set that I presented with the adhesive material that we tested with 3 different types of tests of types of specimens, and there, for doing a comparative study between the materials, we only used what we called in this publication the cleaned data. So data where we removed this type of failures. This type of failures that it might be that this specimen here didn't show any peculiar behavior, didn't fail in the tab, for example, or didn't fail because there was an obvious huge void in the bulk of the material, but still it does not follow my statistical distribution, which is, it's like this, it's below of my statistical distribution. So this data point should not be considered in the statistical analysis. This is a data point that it is censored. We call this a censoring technique. And the censoring technique can be based either on observations. Tab failures, for example, are censored automatically. Specimens that when we check the specimen after failure, we see that there was a huge void at the location of the failure. And because of this, the life was very low. We can censor them. So we have this kind of censoring techniques that are based on observations, but we also have censoring techniques that are based on mathematics. And there we can say, for example, that if we fit a distribution to the whole data set, if a data point is 20% less or 30% less than the average, then we can censor it. Again, this can happen on specimens that are, for example, 50% more than the average. We can even censor the specimens that are showing a very, very much better performance than the total the bulk of the materials that have been tested. So it is not a one-way approach here, and this is obvious, and we have to be very careful when we analyze data, and we should not be biased, if you want, by the fact that usually we don't have so many data to do the statistical analysis. Most of the times, the data that we have are limited, and we should be careful not to be biased by the need to show, to present more data than those that we can really present. So to close this this short discussion here, for me, low scatter is good. However, sometimes low scatter indicates not actually well executed tests, but the opposite, because we might have a very, very small example, and I will close with that. We might have low scatter because all the specimens are failing in the tab. They're failing at a specific load. So then all the specimens will be somewhere in fatigue life for a specific stress rate and for a specific stress amplitude. But this doesn't mean that these data sets so these data points are valid and should be used in the analysis. So again, to summarize this, get your data, but then be critical with your data and use only those data points for which you have a reason to believe that they are reasonable and valid. So we've seen again statistical analysis tools. The discussion that we are doing about scatter is what we've seen here. Between half and 2 decades of life, people believe that this is a reasonable scatter. I would say for me it's more or less 1 decade of life with the experience that we have now with composites. And this scatter is depending on the material and the fabrication. You've seen yesterday these adhesives and the different ways that we use to fabricate. The use of vacuum, so the degassing helps a lot to remove voids. And when you do not have voids in the bulk of an adhesive, then you can expect to have better fatigue results and less scatter in the analysis. So to go back to the description of typical models that we have for fitting of fatigue data, so the SN curve models, we start with the power law and the exponential lines that both show pros and cons, advantages and disadvantages. They are both based on simple hand calculations. You can do it, without the need to use any complicated computer equipment. They are not based on any assumptions, and you can easily apply them. However, they have some problems when we see them on the plot, because the power model, because it is a power exponential equation the power model tends to overestimate the life at very low cycle fatigue, where the exponential model has problems when it goes to the high cycle fatigue, because it's a straight line. And you imagine that if you continue with this straight line, at a certain point, with the model, you will claim that the material will fail at a certain large number of cycles, but will fail even under zero stress, which of course physically it's not possible. So this is what is visualized here. The power curve, although can fit well the behavior of the material between, in this case, 10 to the power of 3 to 1 million cycles, then since it is a power curve, it overestimates the behavior at very low cycles or the static strength behavior that we see in this diagram. On the other hand, the exponential model, which is what we call the lean log, so the equation that is semi-logarithmic, it is a straight line in this semi-logarithmic diagram. We have the number of the stress in a linear axis and the number of cycles in a logarithmic axis. So it is a straight line, which means that if we continue and try to extrapolate our fatigue data, we do not follow the trend of the data, which tend to be asymptotic to the x-axis, but we actually go and hit the axis here, which means that according to this modeling, the material should fail at zero stress when it is at 30 million cycles, which of course physically it's not correct, it's not acceptable. The same we can see in this range. These are the same data sets. And in this case, we used the static strength data to fit the material performance. You see that we lose accuracy with the power model, but it's now better in the entire lifetime. Here again, the exponential, so the lean log model, has the same issue of cutting the axis at a certain number of large material loading cycles. So the wear-out model is the model you remember, the model of Sendesky, that helps to produce curves that are not only based on the power law for the entire lifetime. So they allow to have a sigmoidal curves with multiple slopes, and this helps in certain cases to consider also the static strength, and improves a lot the prediction. What is important in this case where we have this model is to be careful with outliers, the points that we discussed before that are not following the trend. So here, coming back to the previous discussion, here you have a good data set with a closed symbols, and in this data set we have two outliers. And these outliers, although there are only two in a sample of more or less 30 specimens, they can cause problems. If you see here the fitting, the wear-out model with all the data, including these two open symbols, it is the black line, the solid black line. And the same model with the sensor data, so without assuming these two, is the dust line. You can see only by observation that the accuracy is much better for the censored data set. So this is what we discussed, that you should be careful with outliers that affect the behavior. So the wear-out model, you see that it is good for the entire range of points, but the problems that it has is that the problems that can arise with that is necessitating a complicated optimization procedure. So you cannot do by hand this model. You need to run this maximum likelihood estimators for the data, and then you need to do an iterative procedure to estimate the final viable parameters for the model. If you have if you establish a code for that, then it is fine. You can do it. So we've seen before the problems of the exponential model. Here I also show the model. This is the exponential, what we call the semi-logarithmic, and the power model, which is if you like, the log, the double logarithmic model. It's a line in a double logarithmic plot. And we've seen the problems that they have. One is overestimating the life at a low cycle fatigue, and the other one is underestimating actually the life at a high cycle fatigue, the exponential model, when it hits the axis there. So several years ago, we suggested a model that it is a mix of these two. We call it a hybrid model. And actually, we introduced two factors, weighting functions that are factoring actually the mix. And they do a change of the slope at a certain number of cycles, where we call it a transition number of cycles. That is defined in the publication. You will see that it is defined specifically. And if we apply this model, we can see that actually the hybrid model is the one with the solid black line. And we see that to avoid the problems of power, for example, that overestimates this, in this case, we have our model here that changes the slope, follows the slope of the exponential model at the low cycle of fatigue, and then at a certain point it switches and it follows the slope of the power curve. The same happens in another material. Here is glass vinyl ester for glass polyester material. data that we got from different sources. Again, the power law goes very high. The linear model goes low at the high cycle fatigue. Our model is in between and fits better the fatigue performance of materials at the entire lifetime. The same here for strands. So a data set that contained also data up to 10 to the power of 9 million cycles. And this happened because these strands can be loaded at very high frequencies. They are strands of glass and polyester, so they are not fabrics and they are not getting hot when you test them. So you can reach very high frequencies for the testing. And for a typical graphite epoxy, so CFRP material, again, we see that with our model, we can start with good prediction or good modeling. It's not prediction yet. Good modeling of the static strength data, and then follow and switch after a certain point to follow also this asymptotic behavior of the materials when we go to the high cycle fatigue. So this is more or less what we have with the SN curves. And then we go to the CLDs that actually, again, they are models that summarize the results that we have from SN curves. And actually, these models reflect the combined effect of the mean stress and the material anisotropy. The mean stress, it's obvious, they show the mean stress effect by switching from the different SN curves during the diagram, and the anisotropy of the material is reflected because we see different behavior in compression and tension, and different behavior in tensile compressive regions. The CLDs are defined by the main parameters. We have the mean stress axis. The horizontal axis corresponds to the mean stress of the fatigue loading. The vertical axis is the sigma alpha, so the amplitude of the fatigue loading. These radial lines are the SN curves, actually, for specific R ratios. And R ratio, you remember, we defined it as the ratio between the minimum over the maximum cyclic stress. And in the diagram, we can see three sectors. One is the sector for the tension fatigue. The sector in the middle is a combined sector of tension compression fatigue, either tension dominated when we have loads like that are more, they contain more components in tension than in compression, or compression dominated when we have the opposite of this. We have loads that are more in the negative stress. And we have also the area, which is related to completely compressive fatigue. So this is the CLD diagram. So the lines connecting now SN curves, specific points of the SN curves that correspond to the same number of cycles, they are called the ISO cycle lines. And these are the lines that define actually CLD. So here you see typical CLDs, starting with the linear CLD. It's similar to Goodman diagram. You remember Goodman diagram was like that. This is the definition of the Goodman diagram, and all the lines start here from the UTS of the material. So the static, the strength at tensile static strength, and here it goes to the UCS, the ultimate compressive stress. And so this diagram, the linear, has been introduced 15 years ago, more or less, assuming that there are same failure mechanisms between the tension and compression, which of course you see that it's not the case in our material, and assuming the change between this and the Goodman diagram is it assumes here that there is an effect of the time or the loading, even for the case where we have the horizontal axis here. You remember we talked about this yesterday. Here is the case r equal to 1, and this corresponds to a loading which is like that. We have sigma alpha and n. We have a loading like this. We have a very high mean stress, but sigma alpha is 0. So here is 0. And if you plot this in the sigma m, you have a very high mean stress. So this is the case. Of course, there we can expect to have creep, and this is what is considered by this diagram by showing this change here in the horizontal axis. So this diagram is one that has been introduced. It's very simple, but it does not give good results, as you see here, and we'll see also later on when we compare. So other constant life diagram types, it's the typical piecewise linear, and we call it piecewise linear because we draw the iso lines by connecting linearly the points in the different SN curves. Remember, the SN curves are the radial lines corresponding to different numbers of cycles. So this curve might show 100 cycles for all the cases, loading cases. This curve might be 10,000 cycles. This curve might be 1 million cycles for all the cases that have been investigated. We have also a diagram from the group of Harris, Brian Harris, back in the 1980s, where they suggested that you don't have to go linearly or with a different method between known SN curves, so between the radial lines, but you can actually fit an equation, a kind of a polynomial equation that goes from the UTS of the material to the UCS of the material by using the experimental data. So actually fitting these three parameters, F, U, and V of the model. So this M is the normalized stress mean, and this C is the normalized amplitude. Yes, it's the normalized compression strength. This C, and alpha is the output for the normalized sigma amplitude. So if you fit these equations, these three parameters with the data that you can get from at least three SN curves, you can define the model of Harris, and then you can plot. This is a good approach, but it has also some, we've seen with applications for different data, it has some problems. A very simple one, I can already explain that since this is only a mathematical equation, it doesn't take into account any physical mechanisms of the material. In some cases it gives this kind of behavior. It goes below, and this is not possible. It's like doing fatigue testing with a negative amplitude, which physically it's not possible. Fatigue testing is always having an amplitude which is a positive value. So it's this is the mathematical implementation of the model that gives some problems, but in globally it is a good model. It has accurate results. Then it was the group of Kawai, Masamichi Kawai from Japan, that suggested the model which is he used these models to fit actually properties of carbon fiber reinforced polymers that are very stiff, and also highly anisotropic. And he suggested that the model is more or less similar to the model of Goodman, but with nonlinear interpolation between the SN curve at -1 and the ultimate tensile stress and compressive stress. Actually, he suggested to have the peak not at the -1 curve, but to a critical stress ratio that is defined by the ratio between the maximum cyclic stress over the maximum stress in tensile loading. So you will see if you check in the literature, in some cases, this line is not exactly -1, but it might be somewhere. My God, somewhere around this -1 region. And then he suggested that this envelope that he is defining is kind of an envelope that all his CLD is enclosed by the envelope that goes from the UTS to the maximum critical stress ratio and then back to the UCS. There was another CLD proposed by Boerstra. Boerstra was an engineer. It's still is an engineer working with wind energy, and his model is based on the assumption that it's a kind of a modified Gerber diagram, but it does not necessitate the establishment of SN curves. It needs only scarce data, fatigue data of the material at any loading case. And then it has a quite complicated multi-objective optimization procedure to estimate the model parameters. Then we have the piecewise nonlinear that has been suggested by our group. And it was actually the first diagram that was suggested. And it was mentioning that it's not necessary to plot your data on the sigma alpha, sigma m plane, but you can plot also your data on the sigma alpha r plane. And if you do this, the CLD looks like that. Actually, this is a view of this side for this diagram. The CLD looks like that, where again you have four different regions, one for tension, one for compression, and the other two for mixed loading. And they are also a simple interpretation. It's like the piecewise linear, but instead of having linear interpolation between the known values, you have a nonlinear interpolation by parameters that are fitted to the used to the available experimental data. So with this, I summarize the description of CLDs. I didn't do yet comparison, so I showed these models following the models that we've seen for SN curves to show the modeling capacity of CLDs. So now with the CLD, we can say, for example, for this material, that the material is stronger in tension than in compression. So the anisotropy of the material. And we can see also the behavior of the material at different locations. Yet we didn't discuss anything about their prediction capacity and how we use these models for predicting fatigue life. I could suggest taking a break now, because my next slide starts discussing about stiffness degradation theories. Then in the next hour after the lecture of Professor Bedi, I'll come back to discuss about this and then enter the theories that are used for fatigue life prediction. So if there is no question, we can
hello.
Pause. Yes, please.
You were mentioning about like strain rate during static strain test and then the strain rate during fatigue test. Like as you mentioned, less than 10⁻³ cycle, the curve is slightly flat, right? So
Right.
are you suggesting that if we are planning to do a fatigue test at different level of loads, so before that we do the static strain test, like static test at the same strain rate?
What I suggested is what we discussed widely yesterday, is that if you want to mix your static strength data to your fatigue strength data, you should do the tests at similar. You cannot do the test at exactly the same conditions in terms of loading rates, but you should use at least similar loading rates. So this means that you should do actually static strength tests at higher loading rates than those that are designated by the standards.
Okay. We should try to match with the fatigue loading rate.
Exactly. You should see actually not the entire range of the fatigue, because again,
Correct.
in your fatigue SN curve, the rate is different if you keep a constant frequency. Yeah? You have higher rates at the higher stress levels, and you have lower rates at the lower stress levels. So actually your static strength results are corresponding to high stress levels in your fatigue, because you assume that your static strength is the failure at one or half cycle, depending on how you consider.
Correct.
So there you should see what is your strain rate at the first fatigue test that you're doing, and you get, for example, for these 100 cycles or 500 cycles, and you should be able to do a very, very high speed static strength test to estimate your strength to this corresponding to this loading rate that you have in the fatigue testing.
Okay, understood. Thank you.
Welcome. So anything else to discuss, or we can close this first hour? Okay.
I think there is no further questions from the audience. So we can take a break